other sensors like our MRI and many other sensors. For example, in the medical field, when our brain emits signals, it emits signals, and some of the time those signals might not be detected early. And if you have like a neurological disease in the brain, cancer in the brain, the signal changes. But some of those signals cannot be detected unless the disease has developed into a very, very later stage. So my goal is to develop quantum sensors that can be able to sense even the minute signals using the principles of quantum mechanics. So that is my whole project about. So quantum computing with Python is what we'll be doing today. So because most of what we do in quantum computing is based on Python. We design these systems writing Python code. So it's easy for anyone who has a background in Python to easily learn about quantum computing. So I'll give a brief background of what brought us to quantum. So back in the 1920s, every scientist got everything figured out. They know how light behave, they know how this works, they know the motions of particles, they know everything. So they are pretty confident that yes, we've got the whole universe figured out. Then Einstein and Max Planck were working on determining how light behaves. Then they discovered something very, very weird. They saw that this light, they behave like waves and at the same time are particles. They could not determine exactly where those particles are, because if you know their position, you can't know the momentum. So things are very, very pretty weird, and they were very confused about the whole universe. Then at that time, Schrödinger developed an equation called Schrödinger equation. It just described how particles behave and move. And Schrödinger has that equation figured out. Then a scientist called Born was trying to simulate what exactly is happening with light. Then he discovered that lights do not behave in a deterministic way. You can't know exactly where the light is or a particle is. So everything turned from being deterministic to being probabilistic. So it was very weird for scientists to say that, okay, this whole universe is not even deterministic. You can't know exactly where you are at a particular time. Everything is based on a probability. So it changed the whole classical physics world to another side, quantum physics, and people started to work on things relating to quantum physics. So people want to, okay, how do we simulate these systems that are probabilistic? We can't use classical computers to simulate them because they are so much different than quantum physics. So they decided that, okay, if we want to simulate quantum physics, then we need to have a quantum computer. So that is when they started working on designing quantum computers. And right now, we are not yet there, but we are getting there, because there is still a lot of errors, there's still a lot of noise, there's still a lot of things to be figured out. But we are still getting to the stage where quantum computers are beginning to be used for things that are actually worthwhile. So to explain what a quantum computer is, we all know this. A computer, you have your input, you have the system, then you have a output. Then for computers, everything, whether you have images, documents, music, anything at all you have, gets turned to a bunch of ones and zeros, and your computer performs the operation, then you convert it to a language that you understand. Yeah, that is how computer works. So we talk about bits, like everything 0, 1s, they're all bits. We know that about classical computers. And classical computers, we all know, is phones. Everything we use right now are all classical computers. So then come quantum computers. Quantum computers behave in a very different way. We have 1 and we have 0, but we have something called superposition, which is a combination of 1 and 0. So it's a probability. We don't know whether it's exactly 1 or it's exactly 0. So it's a combination of both at the same time. So, and because of that, it gives quantum computers so many other states to compute. It's not just 2 states, it has a lot of other possibilities. So it computes faster than classical computers. So this is what it's explaining. So we know our normal quantum computer, classical computer, when it simulates, we can measure like how long it takes for your maybe computation to like end or occur. But in quantum computer, we are looking at an exponential speed up, such that problems that is taking classical computers 100 years to solve, it will take quantum computers in a matter of hours to solve. And that is something very interesting about quantum computers. So the question is that solving certain problems will no longer take a millennia. It will take a matter of minutes. So these are some of the news and things that people have talked about. We know the traveling salesman problem. If you want to do it with classical computers, you know how long when it's a larger number of cities you're trying to compute. And with quantum computer, because of the possibility, it can try out different routes at the same time. And we believe that with that, you can be able to solve the traveling salesman problem in a matter of minutes. So these are some news we have, like quantum computer has just solved a decade-old problem 3 million times faster than classical computer. That is the true news. The quantum computer built by Google can instantly execute a task that would normally take 47 years. A real news. Physicists find a problem that only quantum computers can do. Quantum computers will break the encryption that protects the internet. Yeah, that is very true. IBM Eagle quantum computer just beats a supercomputer as a complex math. How quantum computer could break 2,408 bits RSA encryption in just 8 hours. Quantum computers will break the encryption that protect, yeah, so many news like that. So about the RSA encryption, we know how they keep our credit card safe. We have like a very long number, and when you are able to factor that number, you can possibly break, yeah, the RSA encryption. But with classical computer, you have to like try out different possibility of the factor of that very large number, which would take so many years. And that is how they've been able to keep our credit card safe, the internet safe, and many things safe. But with quantum computer, because of the possibility of the exponential speed up, you will be able to like find the factor of that number in a matter of minutes. And that is why a lot of funds are going into quantum computing. Banks, government, industry, they are putting in a lot of funds because they want to prepare for the post-quantum time. So you have a lot of things like post-quantum encryption, post-quantum cryptography, such that when we have our quantum computers that are able to break encryption, then everything will no longer work on classical computers beyond quantum computers, because only a quantum computer can break the encryption of a quantum computer. So, and only a quantum computer can protect a quantum computer. So, yeah. Okay, yes. So I'm talking about algorithms that will help protect the encryption. So that is what I'm talking about. Okay, I will try to be faster so that we have a lot of questions after. So yes, so people are like putting a lot of funds into this because we know that in the nearest futures, when there's no more noise in the quantum computer, we would have quantum computers that can be able to do stuff like this. So it's a very interesting field. We have a lot of areas in the field, designing the hardware, writing the algorithm, like a lot of many other field, area in the field. So it's an open call to everyone. You already know Python, so it's all very easy for you to go into the next best thing. Yeah, that's what I call it. It's like the next best field, because in the nearest years, we would definitely have quantum computers almost, maybe not everywhere, but we will have it like very close to us. Don't get me wrong, classical computers will not be outdated. There are some things we will still need our classical computers on, like, maybe designing a flyer, like things like that. You will still need your classical computers for that. But our quantum computer would work, we'll need them when we have so large problem that a classical computer cannot solve that large problem. For example, in AI, it's going to speed up everything we're doing in AI, machine learning, and things like that. So, yes, this is a quantum computer. The whole thing is not a quantum computer. It's just like a small chip. So it's located behind, just at the bottom of the quantum computer. It's just a small chip. The other system is like the dilation fridge, the body. So, okay, for us to be able to get our qubit, which is quantum bit, you have to cool down some of these particles to a very, very, very low temperature. And that is when we see those particles behaving in a quantum way. And that is why we need the dilation fridge. So to know how cold does the quantum processor needs to be, it needs to be cold even than the outer space for it to. So it's like the coldest place on it. And at that time, it easily combines with the environment because it's very volatile. Even a banana peel can destabilize a qubit and make it lose the superposition or quantum properties that make it behave that way. So that is why we still have a lot of noise. So there's a lot of things on like error mitigation. After we've gotten the measurements, there's errors. We try to mitigate the errors, like things like that. So that is what we do right now, error mitigation. It's still noisy, but we do a lot of error mitigation. Then there will be error correction too, which is actually correcting the error before measurement. So this is a video showing like the IBM Quantum Lab, which I would send a link later. We might not be able to watch it. So yeah, qubits are different from bits. As I said, classical bits, 1, 0, only two states. But in qubits, which is quantum bit, we have 0, 1, and we have a combination of 2 states. So the measurement outcome on a quantum system are probabilistic. So it's a probability of maybe 60% of 0 and 40% of 1. And they're in a linear combination of both 0 and 1. So to represent a state of a qubit, we can represent the quantum bit in different ways. We can represent it as a block sphere, a Ket notation, and vectors. So block sphere is just like a circle, and you can only represent like in just a single qubit. When it's multi-qubits, like multiple qubits, you might not be able to represent it with a block sphere. So, and it only works with a single qubit. So the upper state is the 0, and 1 is below, and any other points all around the block sphere are superposition states. So, and we have the Ket notation, which is a Dirac. So it's like a bra and a Ket. So, and we can also represent it as vector. So everything we do on a quantum computer are basically multiplication of vectors, matrices. That is what we do on quantum, in a quantum computer or designing quantum algorithm. They are all multiplication of vectors, matrices, and things like that. So, state of a qubit, block sphere, 0 on top, 1 at the bottom. So, to know, locate a qubit in a block sphere, if it's not 0 or 1, it's in a state of superposition. It's in any other space. So, here at this point, red, it's a superposition state because it is neither 0 or neither is it 1. So, it's in a combination of both 0 and 1. So, we have the plus state, which is pointing here, the minus state, which is pointing up. We might want to take a picture because I will be asking questions after. So anything that is done 0, 1 are all in superposition, a combination of 0, 1. So that is one of the buzzwords you hear in quantum computing, superposition, entanglement, and things like that. So just know that superposition is when the quantum state is neither in 0 or in the 1 state, it's in a combination of both states. So this is just what is describing. Normal computers, you have yes or no. Quantum, well, yes, but actually no. So it's both at the same time. So, okay, I've shown the answer. So the block sphere shows that, which of the block spheres shows that the state has a 20% contribution of 0 and 80% contribution of 1? Which one? We can shout out the answer. So 80 of 1, meaning it's closer to 1 than it's closer to 0. So is what? D? Oh yeah, it's D. So it's closer to 1. So that is closer to 1 than is closer to 0. So which one has a 70% contribution of 0 and 30% contribution of 1? Okay. So it's closer to 0 than it is to 1, yeah. So for the Ket notation, so it's also a very interesting way to show the state of a qubit, because here you can actually describe the superposition, how it works. So this is what, if you have a combination of two states, 0 plus 1, this state is in superposition because it's not in a definite 0 and it's not in a definite 1. So we have something in front, which is called the amplitude of the state. It measures the probability of being in a state 0 or the probability of being in a state 1. So here you can have 60% of 0 or 1, 40% of 1. Both of them all equal to a probability of 1. So this is how a fully 0 state will be like fully 1 as the amplitude and 0 as 1. So, and this is a fully 1 state, and this is a combination of both, because when you find the addition of both, it will give us 1. So we have different quantum gates, which we will implement quickly today. So there are like many different quantum gates. We have the Hadamard gate, which creates the superposition, S gate, we have Y gate, we have many gates. They are just like having like the quantum counterpart of a classical gate. So some of them, we don't have it in classical world, like the H gate. We don't have that in the classical world. So the X gate is just how it behaves in the classical world. 0 turns to 1, 1 turns to 0, and this is it, a rotation around the Bloch sphere. So when you have X, 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 you turn it to like 1, and after that, 0 back. So you know this is having the 0 state, and this is also this 0 state. So as I said, we can all represent a quantum state as vectors. The Hadamard gate is what causes superposition. If you have 0 state, it turns it to a plus state, which is neither 0 or 1. And if you have 1 state, it turns it to a minus state, the other way around. So this is what the Hadamard gate does, superposition. So I would quickly jump to this so that we'll be able to do a bit of coding. So yeah, another concept I have to explain is the entanglement. It's a very, very interesting concept. Two particles, no matter how far they are, even if they are at the end of the world, far apart from each other, no matter how far they are, when they are entangled, the state of one affects the state of the other. So if you do something on one, it immediately affects the other. At first, scientists were saying that, okay, this is a faster than light communication, but actually it's not faster than light. It's not at all faster than light, but it's like an instantaneous like communication. So right now, there's a lot of work going on designing communication, secure communications through entanglement, because through that, you will know when something is happening in the system. When that is how they're trying to build like a lot of post-quantum algorithms for encryption. So when you try to like check what is happening in a system, the other system knows it and break it down. Because when you check the state of the system, the other system knows. So with that, you can't spy onto through a quantum network. So we have many other gates, the H gate. They basically do the same thing. The measurement. So measurement is the last part. When you measure a quantum circuit, it forces it to take a state. So then it's no longer probabilistic, it's now deterministic. It either choose 1 or 0 when you measure. So that's like the final state. So it determines like the one with the higher probability. If you have one with a higher probability, it chooses the 1 state. If it's 0, that is with the higher probability, it chooses the 0 state. So then we have multi-qubit gates that can work on 2 qubits, which one is C0. It just works like some of our classical gates. So we have the control qubit and the target qubit. So if you have your control, which is, if your control is 0, so it will do nothing on the target. If your control is 1, it applies an S gate to the target and flips it. So that is what happens. So for here, because the control is 0, it will do nothing on the target, and the target remains 0. So down to the code. So I'll just show how to design quantum circuits using Python. So here are some of the codes we need to know. So if you want to see what I'm doing, it's on this. If you want to use your system to see what exactly I'm doing, you can check it out here. So if you want to run it on the real hardware, IBM has a lot of hardware on cloud. So you have to set up your account on the cloud, get an API key and things like that, which is easy. So, but you have your quantum simulator. If you don't want to use the hardware, you can simulate it. It's like an ID measurement when there's no noise in the system. But when you use the hardware, you have to account for the noise in the system. So what we'll be doing mostly, we'll be using the simulator, where it's like an ID measurement. So these are some of the packages I need. QuizKit is a very good package built by IBM for designing quantum circuits. So you can visualize the quantum circuit, you can simulate the quantum circuit, you can also run it on their hardware using the IBM runtime. Then you have the transpiler, because sometimes you might want to design your own quantum circuit, and those gates might not be available on the IBM hardware, so you have to transpile it to the gate available on the IBM hardware. So to create a quantum circuit, you have to create your quantum register, which means the quantum bit, and you have to create a classical register, because any measurement you do on the quantum register, it has to be saved on a classical computer. So you can't just create your qubit without having a quantum register. So everything you measure will be saved on the classical register. So that's why I said we can't totally eliminate a classical computer, because a lot of post-processing happen on the classical computer. So to create the quantum circuit is a combination of both the qubit quantum register and the classical register. To apply an S gate, you just apply X on whatever qubit. So here we're creating a quantum circuit with just one qubit. I define it as 1 here, and we created the classical register as 1 register 2. Then we created the quantum circuit. To apply S gates is just applying X on the qubit you want to apply it. You can also do it this way: 1 qubit and 1 classical register, and apply S gates on the first qubit, counting from 0. So we can visualize the circuit by drawing it here. So this is some exercises you can do on your own if you want to try to design your own quantum circuit. So you can also visualize it. From here, I apply an S gate to a quantum circuit. Something to know is that the original state of a quantum system is in state 0, the ground state. Everything starts from state 0. So when you apply S gate, it flips it to state 1. So after visualizing when applying the S gate, we can see it's no longer on qubit 0, it's now on qubit 1. So you can visualize it also using this. So you can also apply your measurement. As I said, when you measure a qubit, you must attach your classical register to it. So when you measure it, it gets saved on the C register. So it just shows us here, we measure the Q-reg and it gets saved on the Q register. Then you can execute the circuit using the backend. Here I'm using the simulator, the backend simulator. So, and we can also visualize it using this to just see the amplitude of the state. Here it's telling us that it's state 1, definite state 1 after measurement, because it was in state 0, you apply X to it and is in state 1. You can visualize the final states using different visualization. You can also do a lot of rotations on the block sphere. You might not use X gate and say X gate rotates like the full 180. You can do rotations that are 90, 45 degrees using the RS gate, RY gate. Then the C naught gate is the entangling gate. It does like the real entanglement. So you can do different rotation X, Y, and Z using these gates. Then if you want to create your own parameter, this is how we do a lot of quantum machine learning algorithms, because we want to embed our data set into the gate of the quantum circuit. So you can define your own parameter, and this parameter can be anything. Can be the picture you are trying to embed, or maybe a data value you are trying to embed. And one thing you have to do is to, when you have a classical data set, you convert it to a quantum data set using this embedding, using any of the gates. You embed it, and then you can do your quantum machine learning process. So yeah, so to actually run it on the hardware, you have to have your API key and this CRN, and you create your instance, which is also like a template that you can use. Then after that, you can now decide to like run it on the quantum computer. You measure it, you simulate it, you sample the results, and you can plot the final results. And also do post-processing. So here you can actually transpile it before you run it to the actual hardware. So this is important when you are using the actual IBM hardware. You have to transpile it before you can be able to run it. Yeah. So that is just any question? Okay, yeah. So presently CSU, there's a lot of research efforts going on in CSU on quantum computing. We have Satish Kumar, which is my advisor, working on a lot of research related to quantum, Meduramatis, and Chansiyu. Chansiyu is actually having a micro course presently that is starting on quantum computing, and we'll be having a quiz kit fall fest all through this fall from September to December. We'll be having workshops, weekly workshops on quantum computing. We'll be visiting the Cleveland Quantum Computer. We'll be having sessions, hackathons, and things like that all through this fall, and it's sponsored by the IBM. So if you're interested. So yeah. Any question?